Hello everyone. So in today's video, we are going to go over the remaining parts of this prompting survey paper. So we have reached topic 9, which is prompt relevant topics, and let's just try to finish this paper up in this video. All right. So in this section, we connect prompt learning with other similar learning methods. So first we have ensemble learning. It is a technique that aims to improve the performance by taking advantage of the complementarity of multiple systems. So generally the different systems result from different architectures, training strategies, data ordering, or different initializations. So in prompt ensembling, the choice of prompt templates becomes another way to generate multiple results to be combined. And this has a clear advantage that this does not necessarily require training the model multiple times. For example, when using discrete prompts, these prompts can simply be changed during the inference, and you don't really need to train it with different prompts. Then you have few shot learning. Few shot learning aims to learn a machine learning system in the data scarce scenarios with fewer training examples. There are a wide variety of methods to achieve few shot learning, including model agnostic meta learning. Then you have where you learn features rapidly, adaptable to new tasks. Then you have embedding learning, embedding each sample in a low dimensional space where similar samples are close together. Memory based learning, so representing each sample by a weighted average of content from the memory, and so on. So prompting augmentation can be regarded as another way to achieve few shot learning. So where you are priming based few shot learning. So compared to previous methods, prompt augmentation directly preprints several labeled samples to the currently processed sample, elicit knowledge from pre-trained language model even without any parameter tuning. So you just show it a few samples and then the model learns to okay, the model learns, okay, this must be expected out of me. So we have this table. Uh, so these are just some research topics. I guess you can go over them yourself. These are pretty self-explanatory. Then larger context learning. Larger context learning aims to improve the system's performance by augmenting the input with additional contextual information. So this can be retrieved from the training set or some external data sources. So for instance, in the case of say Twitter, say some Twitter sentiment analysis, the user's previous tweets or the user's bio might be a relevant feature which you can extract from external data sources. Prompt prompt augmentation can be regarded as adding relevant labeled samples into the input, but a minor difference is in larger context learning. The introduced context is not necessarily labeled data. It can be anything, right? So, for instance, the user's bio is not related to the tweet directly, but it's just information. Then you have query reformulation. Query reformulation is typically used in information retrieval tasks and Q&A tasks, which aim to elicit more relevant text or document or answers by expanding the input query with related query terms or generating paraphrases. So the same prompt would here in terms of prompt, you'll just have the same prompt in different ways. So there are several commonalities between prompt-based learning and query reformulation. So both aim to make better use of existing knowledge bases by asking the right questions. The knowledge bases are usually black boxes not available to the users, so researchers must learn how to probe it optimally based on solely the question which the user asks. So there are also differences. The knowledge base is traditionally query in traditional query formulation problems usually a search engine, or a QA system. By contrast, for prompt-based learning, this knowledge base is an LM, and we need to find the appropriate query to elicit an appropriate answer from it. So the input formulation, reformulation in prompt learning has changed the form of task. For example, an original text classification task has been converted into a closed question problem, therefore bringing additional complexity. So you need to formulate it well, you need to change the modeling framework accordingly. So maybe just looking at the CLS tokens embedding is no longer the solution, right? You need to opt for a MLM and so on. These steps are not required in traditional query formulation. Despite these discrepancies, some methodologies from query reformulation research still can be borrowed for prompt learning, such as decomposing input query into multiple subqueries, which is similar to how to decompose prompts, which we saw before. So QA-based task formulation. QA-based task formulation aims to conceptualize different NLP tasks as a question answering problem. So Kumar et al., McCain et al. Are earlier works that attempt to unify multiple NLP tasks into a QA framework. Later, this idea has been further explored in information extraction and text classification. These methods are very similar to the prompting introduced here in that they use textual questions to specify which task is to be performed. However, one of the key points of prompting methods is how to better use the knowledge in pre-trained language models, and these were not covered extensively on previous works advocating for QA formulation. So you ask the model uh, the query in form of a question and don't really care about optimally probing the model's factual storage. Then control generation, it aims to incorporate various types of guidance beyond text into text generation models. So specifically, guidance signal could be style tokens. So for style transfer, length specifications, domain tags, or any variety of piece of information used to control the generated text. It can also be keywords, relation triplets, or even highlighted phrases or sentences to plan the content of the generated text. In a way, many of the prompting methods described here are a type of control generation where the prompt is usually used to specify the task itself. Thus, it is relatively easy to find commonalities between the two genres. So, both add extra information to the input text for better generation, and these additional signals are often learnable parameters. And if control generation is equipped with sequence to sequence based pre trained model like BART, then it can be regarded as prompt learning with input dependent prompt and a prompt plus language model fine tuning strategy because you're training both BART and the prompts. So, one example is GSUM, where both the prompts and the pre trained language parameters can be tuned. Also, some clear discrepancies are there. So, in control generation work, the control is generally performed over the style or content of the generation, while the underlying task remains the same. They don't necessarily require a pre-trained model. In contrast, the main motivation for using prompts is to use the pre-trained models, right? So you only want to specify the task and better utilize the pre-trained model. Moreover, most of the current work on prompt learning and text generation shares a dataset or task level prompt. Only very few works have explored input-dependent ones. However, there is common setting and effective. There, this is a common setting and effective in the control text generation, which may provide valuable direction for future work. So, what does these last 2 points mean? What do these last 2 points mean? So, for the second point, the current works in prompt learning share a data set or a task level prompt. So, these are the prompts are specific to say sentiment analysis and so on. Only very few features have works have explored input dependent ones. So you don't really change your prompt based on the input itself. So if you're doing sentiment analysis, all of them will follow the same template in most cases and won't change based on what the input is. So for supervised attention, knowing to pay attention to the important information is a key step when extracting useful information from objects such as long text sequences, images, or knowledge bases. So supervised attention aims to provide explicit supervision over the attention of models based on the fact uh, complete, completely data-driven attention can overfit to some artifacts. So in this respect, prompt learning and supervised attention share ideas that both aim to extract salient information with some clues which need to be provided separately. So to solve this problem, supervised attention methods try to use additional loss function to predict goal attention on a manually labeled corpus. Research and prompt learning may also borrow ideas from this literature. So this is some, if you're familiar with the Hate Explain paper, they also do something like this only. So I'll just show you a diagram to explain. I believe that will be the fastest way. So when you just leave attention to learn the model to learn the attention weights on its own, it might learn some spurious correlations. You might want to force the model to learn in some particular way. So you can annotate your data to know which words the model should pay more attention to, and then use that. Uh, Let me just go to the right figure. Yeah, use that predicted attention over the words and the attention which is the grounded attention which you manually annotate and compare them and try to bring the predicted attention close to the grounded attention. So this will force the model to not learn spurious attention relations. Right. For data augmentation, it is a technique that targets increasing the amount of data that can be used by making modifications to existing data. As recently observed, adding prompts can achieve similar accuracy improvement to the addition of hundreds of data points on average across classification tasks, which suggests that using prompts in a downstream task is similar to conducting data augmentation implicitly. So maybe different prompts query different chambers of the model's brain finally. So we finished section 9. Now we'll moving on to section 10. Section 10 is on the challenges. So for prompt design, tasks beyond classification generation, most existing works about prompt-based learning revolve around either classification or generation because they are the most important ones and the most used ones as well. Applications to information extraction and text analysis tasks have been discussed less, largely because the design of prompts is less straightforward. We expect that applying prompting method to these tasks in the future will require either reformulating or that they can be solved using classification or text generation based methods or performing effective answer engineering that expresses structured outputs in an appropriate textual format. So just adapting to newer different methods. Prompting with structured information. So in many NLP tasks, the inputs are imbued with some variety of structure, like a tree, graph, table, or relational structure. How to express best these structures in prompt or answer engineering is a major challenge because you want to give optimally probe the model's information, right? So existing works make a step by making prompts with additional marks to encode lexical information such as entity marking. Agha et al. 2021 presents structured prompts based on hypertext markup language for more fine-grained web text generation. So I guess they are giving it H1 tags and so on, so it knows what it needs to generate, right? Because the model has seen a lot of HTML documents as well. However, moving beyond this to more complicated varieties of structures is largely unexplored. So maybe this could be like a SQL query or a knowledge graph query. Entanglement of template and answer. The performance of a model will depend on both the templates being used and the answer being considered. How to simultaneously search or learn for the best combination of template and answer remains a challenging question. So current works typically select answers before they select template. Uh, typically select answer before select template, but the work by Hambad Zumian et al. 2021 have demonstrated the initial potential of simultaneously learning both. So learning the answer and the templates together. Then you have answer engineering. So these were all for prompt designing. Now for answer engineering, you have many class and long answer classification tasks. So for classification based tasks, there are two main challenges. When there are too many classes, how to select an appropriate answer space becomes difficult. Uh, and when using multi-token answers, how to best decode multiple tokens remains unknown. Although some multi-token decoding strategies have been proposed. So if you want to say decode two tokens in a blank, how would you do that in the most optimal way? Multiple answers for generation tasks. So for text generation tasks, qualified answers can be semantically equivalent but syntactically diverse. Because you can have multiple ways to answer the same thing. So far, almost all works use prompt learning for text generation, relying solely on a single answer with only a few exceptions. How to better guide the generation process with multiple references remains a largely open research problem. And then the selection of tuning strategy, as selected discussed, you have a variety of tuning parameters of prompts, language models, or both. However, given the nascent stage of this research field, we still lack a systematic understanding of the trade-offs between these methods. The field could benefit from systematic exploration, such as those performed in the pre-trained and fine-tuned paradigm regarding the trade-off between these different strategies. So these are all the problems with or the challenges with learning your answers. So answer engineering. Then for multi-prompt learning, you have prompt ensembling. So in prompt ensembling method, the space and time complexity is pretty high. How to distill the knowledge from different prompts remains unexplored. So some works use an ensemble model to annotate a large dataset to distill the knowledge from multiple prompts. In addition, how to select ensemble-worthy prompts is also underexplored. So for text generation, the study of prompt ensemble learning has not been performed so far because some ensemble learning in text generation itself is relatively complicated. To remedy this problem, some recent proposed neural embedding and ensembling models such as refactor could be considered as a method for prompt ensembling in text generation. So essentially, the issues with prompt ensembling. Then you have prompt composition and decomposition. Both of them aim to break down the difficulty by introducing multiple sub prompts. So in practice, how to make a good choice between them is a crucial step, because if you create worthless sub prompts, then your downstream performance decreases. So empirically, for token or span prediction tasks, prompt decomposition can be considered, while for span relation prediction tasks, prompt compositions would be a better choice. In the future, the general idea of decomposing or composing can be explored in other scenarios apart from just NER or entity co-reference resolution. Now, prompt augmentation. Existing prompt augmentation methods are limited by the input length. So, feeding 2 minute demonstrations to the input is feasible, because then your attention is very uh, split up, right? So, it doesn't really pay, it might not pay the right amount of attention to every word where you really want the attention to be. And it might again start suffering from like long range problems. Therefore, how to select informative demonstrations and order them in an appropriate is an interesting but challenging research problem. For prompt sharing, all the above considerations refer to the application of prompt in a single task, domain, or language. We may also consider prompt sharing, where prompt learning is applied to multiple tasks, domains, or language. Some key issues may arise, including how to design individual prompts for different tasks and how to modulate their interaction with each other. And this hasn't been explored yet, so having common prompts across tasks. Then, of course, you have the issue with selecting pre-trained models. You have a lot of pre-trained models, and you do without trying, it's really difficult to choose which one you should use. But again, you can choose them on the basis of say your task. So an autoregressive model might be better for prefix prompts and so on. Then you have theoretical and empirical analysis of prompting. Despite the success, theoretical and analysis and guarantees are scarce. So we at all show that soft prompt tuning can relax the non-degeneracy assumptions, like the generation probability of each token is linearly independent, needed for downstream recovery. That is, recover the ground truth labels of the downstream task, making it easier to extract task-specific information. Saunshi et al. Verified that text classification tasks can be reformulated as sentence completion tasks, thus making language model a meaningful pre-training task. Language modeling. Scow and Rush empirically show that prompting is often worth hundreds of points on average across classification tasks. So these are just some analysis, but there is not a lot of analysis. Then you have transferability of prompts. So understanding the extent to which prompts are specific to the model and improving the transferability are also important topics. So would the same prompt which works for GPT-3 work for GPT-2 or GPT-Neo? These are some interesting questions. Perez et al. Showed that prompts selected under tuned few-shot learning scenarios, where one has larger validation set to choose prompts, generalize well across models of similar size, while prompts which are chosen in truer few-shot learning scenario do not generalize quite effectively. The transferability is poor when the model sizes are quite different in both scenarios, because then I guess like this is just an intuitive explanation, but you might be querying in different spaces in some sense, because your information might be more sparsely located in the model's neurons. So combination of different paradigms. Notably, much of the success of prompting paradigm is built on top of pre-trained models such as BERT. However, are the pre-training methods that are effective for the latter applicable as is to the former, or can we entirely rethink our pre-training methods to further improve accuracy or ease of applicability to prompt-based learning? So this is one task. A lot of people might not be doing this because first of all, it's really hard to retrain a model. It's very expensive, very time taking, and it's very hard to justify as well in some sense, because these models are extensively used in other tasks apart from prompt learning. So creating prompt specific models, unless you have very strong guarantees of generalizability, would be very hard to justify. So now calibration of prompting methods. Calibration refers to the ability of a model uh, to make good probabilistic predictions. So when using the generation probability of pre-trained language model to predict the answer, we need to be careful, since the probability distribution is typically not well calibrated. The Jiang et al. Observed the probabilities of pre-trained models like BAR, T5, GPT-2, and QA tasks are well calibrated. Zhao et al. Identified three pitfalls. So you have a majority label bias, recency bias, and common token bias. So these lead to the most common biases. For example, if the final answer prompt has a positive label, then this will bias the model towards predicting positive words. So this is because this is where your ordering of prompts and choosing right prompts comes into play. To overcome these pitfalls, Java told you first use context-free input. So the prompt would be input, subpar acting, sentiment negative, and then so on to get the initial probability distribution P naught. And then they use a real input. Example, the prompt would be input subpar acting, sentiment negative, beautiful film, sentiment positive, to get the probability distribution P1. So here you haven't yet given the input in the first case, but you have in the second case. Finally, these two distributions can be used to get a calibrated generation probability distribution. However, this method has two drawbacks. It comes up with the overhead of finding proper context-free prompts like whether to use NA or none, things like that, and the probability distribution of the underlying pre-trained language model is still not calibrated because you're just tuning it on a higher or a more higher level of abstraction, not really tuning the language model itself. Even though we have calibrated probability distributions, we also need to be careful when we assume a single gold answer because there could be multiple answers. For example, if we consider the gold answer to be whirlpool bath, the generation probability of it will typically be low since the word bathtub shares the same meaning and it has occurs more frequently, so it has a larger probability mass. So to address this issue, you can perform answer engineering to construct a comprehensive gold answer set or calibrate the probability of word based on its prior likelihood within the context. So these are just all the challenges which we currently have with prompt-based learning. Next, we go on to some meta-analysis. In this section, we aim to give a quantitative bird's eye view of existing research by performing a meta-analysis over existing works. So this is a timeline. The time for each paper is when it was posted, and red considers NLU, blue is NLG, and green is both. Okay, so I see a lot of red, so a lot of NLU tasks. Um, right, so the timeline. Okay, so these are just some general things, not really related to prompt learning itself, but how it has developed, I guess. So we first summarize the existing papers in chronology. So you have years, you have the tasks which to take on, then you have automatic search. So how many use automatic search for template finding, and then you is your search space continuous or discontinuous. So these are all very interesting to see. You can see like the continuous answer search space only arose in 2021. So tasks, so these are the commonly used tasks, so like text classification, factual probing, and so on. Then you have prompt versus answer. So these, I guess, these plots are very self-explanatory. I won't be going over them. Finally, you have your conclusion. So in this paper, they have summarized extensively. They have mentioned, they have extensively covered all the different things, all the challenges, all the different methods already existing and the challenges associated with them. So I guess we don't really need to read the conclusion if we've read the work so far. And I hope this inspires you to do some work. This certainly inspires me to do some work. And this has probably been the longest paper I've ever covered on my channel. This is already the fourth part, and this video already is around 25 minutes long. So I'm just thinking I'll just upload this as a fourth part, and then for people who might be interested in finding one video covering the whole paper, I'll create all of them combined into one video. So these are just the language models and their sizes and so on. So thank you guys for tuning in. Hope to see you again in future videos as well.